Okay, we're into the third video on energy. We're going to look today a lot more at conservation of energy, specifically within systems, open and closed systems, talk about conservative or non-conservative forces. So we had already established that conservation of energy is this idea energy is not created or destroyed. It simply changes forms or types of energy. So all the energy that exists around us is just constantly changing through the processes of work. And work is force acting parallel to displacement, which causes those changes in energy to happen. So you have some potential energy, then some work happens that turns into kinetic energy. Okay, now you've got kinetic, and then there's more work that happens, and maybe your kinetic energy turns into thermal energy. So all these processes that happen in the entire universe are all because energy, through the process of work being done, changes forms from one type into another. And conservation just says, while that's happening, none of that energy goes away entirely. It's not destroyed. None of that energy comes out of nowhere and is suddenly appears. It's just the same amount of energy that's changing from one type to another. And that law of conservation, we can also abbreviate law of conservation of energy, just so you don't have to write out the whole thing. Um, but we looked at it last time, the way to write it as an equation. So we'll start with that. It says the starting amount of potential energy, so initial potential plus initial kinetic, plus any work that is done by external forces that we're about to look at when we look at open and closed systems, um, is equal to the final potential plus final kinetic. Now, these could be um, spring potential and or gravitational. Same thing here. So this is just a short general way to write conservation of energy, but you could start off at whatever initial spot or point you're looking at. You could start off with spring potential or gravitational potential. Same thing at the second place you choose to look at. You could have spring and or gravitational. Now, a couple notes on conservation of energy is that this can be used for any 2 points in a process. It can be used to look at any 2 points in a process. It certainly could be the very beginning and very end of whatever is happening. It could be that your initial is right at the beginning of something starting from the top of a hill and sliding down, and then your final potential or kinetic energies are at the bottom of the hill right as it reaches the bottom. But you could just as easily use this to look at the energy at the top of the hill and then the energy halfway down, or you could start halfway down and then go to 3/4 of the way down. So you can pick any 2 points throughout a process and say at point number one and at point number two, we can compare the amounts of energy, also bringing in work. But to really do all that, we need to understand systems and how they play into energy in terms of open and closed and internal or external forces. Now, we already have a little bit of an idea of systems from Unit 2. We had like Atwood's machines or multiple objects that were all part of our systems. And we considered forces. And we said, all right, what forces are acting from inside the system, internal forces? What forces are acting from outside the system, external forces? So we've already got a bit of a baseline for that. And so for energy, systems are really just the same kind of thing. System is, multiple things, multiple objects that are combined together to make up a system. Systems for energy consist of multiple objects. Um, well, it doesn't have to be more than one. You can actually have we'll say one or more. You can have systems where you only have one object actually, which is kind of interesting. So one or more objects uh, with either internal or external forces acting. And can be open or closed. So we'll define what those things are. We'll get a review of external, internal forces. Okay, so remembering from Unit 2, this should be also in your notes for Unit 2, that internal forces act from within the system, objects that are within the system pushing or pulling on each other, external forces acting from outside of the system. Something from outside of the objects in the system is pushing or pulling on the objects that are in the system. Okay, so before we, well, yeah, we can talk about open and closed first, and then we'll talk about like specific types of energy and how that plays in. So open systems means that external forces from outside of the system uh, can act and do work energy can enter or leave the system. So we said energy isn't created or destroyed, which is absolutely true. What energy can do is if we look at the energy of just one object, like a basketball flying through the air has some kinetic energy. And maybe we only include that in our system. We say it's just the basketball. Our system is going to be just the basketball by itself. And then someone catches the basketball. Well, that person's force, their applied force from their hands catching the ball, were outside of the system, which is just the basketball by itself. And so they put an external force on the ball. They did work on the basketball, and energy then entered or left the system. Because all of that kinetic energy that the basketball had is now, well, it no longer has it if it's caught and the person is standing still holding the ball. So open systems mean forces from outside of the objects on the system can act on the system, can do work, and can change the amount of energy that's in that system. This goes back to our conservation equation. If you had that example of maybe the ball doesn't really have any potential energy, or maybe it does, but it has maybe some potential energy, and it definitely has kinetic energy if it's moving. I guess if it's above the ground, you could look at gravitational potential energy for the basketball. But anyway, the main focus would be it has a lot of kinetic energy as it's moving. Then this person from outside does some work on it. In the case of stopping the basketball, it would actually be negative work. Because if the ball's flying through the air, like to the right, for example, the person's force would be to the left. And our work equation from the last video showed us that if force and displacement are in opposite directions to each other, you get negative work. So we'll see examples, and we'll go through these as we work through problems and whatnot. We'll see examples of either positive or negative work. And in the case of negative work, what happens is you had all this kinetic energy that an object had while it was moving. If negative work gets done on that object, then it doesn't have nearly as much kinetic energy left at the end. So that's energy entering or leaving a system. As you might say, we have a lot of energy at the beginning in our system. By the end, we don't really have that much because there was negative work done. On the other hand, you could have someone come in from outside the system and they could do positive work to speed up the object and give it more kinetic energy. Um, if you have a ball like a soccer ball rolling on the ground and you come along and you kick it and make it go even faster, then the ending kinetic energy would be more than the starting kinetic energy if you do positive work with a force in the same direction as the displacement. So there's options here of open systems mean that forces can come in from outside of the system doing work, and at the end, after that work happens, you could end up with more energy than you had before in the system, or you could end up with less, depending on whether those forces did positive or negative work. Okay, closed systems are much more simple because closed means no external forces do work on the system. Interestingly, physicists maybe go back and forth on this. I generally would expect no external forces to be acting at all in a closed system. You could, in theory, have external forces that are present. There are pushes and pulls from outside the system that are acting. Um, but they don't do any work. An example would be if a ball rolls along the floor and gravity and normal force act on it, but gravity and normal force never do any work on the ball because it doesn't move up or down with any displacement, then there's no work from those external forces at all. Um, so no external forces are doing work on the system. No energy enters or leaves the system. All right, so going back to our conservation equation, I'm going to slightly edit it for the purpose of closed systems. So for closed systems specifically, it would just be potential plus kinetic at the beginning equals potential plus kinetic at the end, because you don't need to ever include that work from external forces. So conservation of energy means that exactly as much energy in total that you had at the beginning is the same total energy you have at the end because there was no external work whatsoever from those external forces. So all the energy that started in the system is still in the system at some later point in time. Okay, so that's open and closed. Is if you have forces acting from inside the system, internal forces, that's fine. They can do work in open or closed systems. But outside external forces, only do work in open systems. Closed systems means there is no work at all from those external forces. And with the open system, you have energy that can enter or leave. You could end up with more energy at the end than the beginning, or vice versa. Closed systems, you just no energy enters or leaves at all. You have the same total amount of energy at the beginning and the end of whatever's happening in a closed system. Okay, cool. Um, let's look a little bit at energy types for systems. And we'll look at possible, well, we'll say energy types that exist in a system based on the objects within it or the objects in it. So what objects are in our system affects what types of energy we're going to see within that system. So let's start with gravitational potential energy. For that, we need at least an object Earth system. Because gravitational potential energy is always based off of where the object is relative to the Earth. Because the Earth is the thing providing, right, the gravitational force that pulls on it. So gravitational potential energy exists on the Earth because the Earth is pulling on the object. So we need to know, even though for gravitational potential energy, we have an option of with horizontal zero lines, it gives us a way to define like this is where we're choosing the height of zero to be. And even though that may not be the actual like floor or ground, um, we can pick a spot to say, all right, anything above this spot has positive gravitational potential energy. If something is at that line or at that height, the horizontal zero line, we have no gravitational potential energy. But you need an object Earth system in order to have UG. If you have a system that consists of only the object, what happens is, so we'll add that in here. For systems of only an object by itself. So they might say, consider the system consisting of only this object, not including the Earth. In that case, force of gravity is an external force acting from outside of the object itself, the Earth pulling on the object, um, doing work external. And that means your system is open. So if you have a problem where gravity is acting because an object is near the surface of the Earth, of course, gravity always acts when things are near the Earth. Um, if you have the system consisting of only the object, then gravity means the system is open because there is a force. Um, Now, if the object doesn't move up or down at all, if it remains at the same height, then there's no displacement up or down, and then there's no work being done. So that's sort of a loophole of like, if your system is only the object, um, then the system is open if, well, yeah, we'll get into some problems that deal with the definition. Their definitions are a little bit interesting when it gets to like what's open and what's closed um, and whatnot. So yeah, we'll talk about that and some problems. But the system is open if you have an external force doing work. Gravity would be an external force outside of your system if it's only the object. So really what we're looking for is if you want to have a problem where you're working with gravitational potential energy and you say, all right, I want to find how much energy, potential energy exists here for an object sitting on top of a cliff or at the top of a ramp or dropped from some height. All of those gravitational potential energies require that you have an object Earth system. If Earth is not part of your system, then it's open. Okay. And not only is it open, but you can't have that gravitational potential energy present in your system unless Earth is part of it. Okay, other things, kinetic energy. This one's pretty simple. We simply need an object. As long as there is an object that is moving, then you have kinetic energy in your system. So if you had a system consisting of only the object, sure, you could have kinetic energy in that system. That's fine. As long as the system includes the object that's moving, then you have kinetic energy within that system. Versus UG, gravitational potential, right? You need to have both the object and the Earth in that system, part of the system, in order for UG to be there. Okay, and then spring potential energy. Well, we need a spring, specifically a stretched or compressed spring, I guess, because if it's at its natural length, then it won't have any stored energy in it. So stretched or compressed spring. That's pretty much it for spring potential. AP's a little bit flaky on their definition for this, where I've seen a couple times where they want to have the spring and the object both be in the system, but really the energy is stored within the spring itself. Um, I'll put in parentheses here. You could say like, or spring object is very common for the object itself being included within the system. But in reality, I mean, the energy itself, the stored energy, is just because of the spring being stretched or compressed. So, I would personally not say that you need to have a spring object system in order to have spring potential energy show up in your system. One quick thing to note is E thermal is not in the law of conservation of energy equation. Because of that, so something like friction that produces thermal energy, if you've got force of friction acting, doing work, oops, I drew an arrow for some reason. If you've got force of friction, or you have some drag force that also produces thermal energy. So heat and sound are produced by the work of friction or the work of drag. And if you have those things present, uh, those forces doing work mean that your system is open. So let's talk about the reason for that. The reason that friction or drag doing work means your system is open is that thermal energy cannot show up in this equation. Even in the open system one, we've got potential, gravity or spring. We've got kinetic, initial and final there, but we don't have thermal. So anytime that friction or drag, or it could be some other force, but those are really the main two that produce heat and sound for thermal energy as far as work is concerned. When those forces do work, it will be external work. Not only that, it'll end up resulting in thermal energy. So this equation doesn't have thermal in it. We'll talk about a little bit with conservative and non-conservative forces later on, where um, conservative and non-conservative forces have to do with energy going back and forth between potential to kinetic and then kinetic to potential. Um, Thermal energy, once you get some thermal energy that's changed from kinetic into thermal through the work of drag or friction, we really can't go back and just take that thermal energy and easily like turn it into kinetic or potential energy. So open systems mean once that energy change occurs and you get thermal energy from heat or from drag or friction, then this external work would be some negative amount that just produces or changes kinetic energy into thermal. And then at the end, you've got some extra thermal energy. So in theory, you could like do plus E thermal. It's not that you couldn't ever do that and say, well, if we end up with some thermal energy at the end due to the work of friction, we could account for that. It's just those systems where thermal energy, where we change kinetic into thermal through drag or friction, they're going to be open systems because we're going to have external work from those forces of drag or friction outside of the system. So you're not going to see thermal energy show up in the potential energy initial or final, or in the kinetic initial or final. Even though thermal is sort of a subtype of kinetic energy in that it's motion, it's the motion of small particles, we're not really going to see that. So E thermal is not in the law of conservation. Any friction or drag doing work mean the system is open. Okay, let's see. I think that's mostly it for systems. We went over open and closed, external, internal forces, and internal forces can do work. So we'll just add a reminder there just in case there was any question of like, um, internal forces in a system can do work. It's it's not that you can't have work from those internal forces. You absolutely can. Um, but what happens then is it does work to go between. Already running out of space. I feel like I'd written that much, but maybe I'm already running out of space here. We're running out of characters. Go between potential and kinetic energies. So if you have a force from inside your system that's acting to do work, what we're going to find is that that's going to either convert potential to kinetic or kinetic to potential, and we're just going to kind of go back and forth between those two. This also leads us into conservative forces. So these internal forces are conservative. All right, so what do conservative forces mean? Let's address that. All right, so conservative forces, common examples would be the force of gravity and the force of spring. Those are a couple very common conservative forces. These forces do work to convert between potential and kinetic energies. Now, keep in mind that could be potential gravity, it could be potential spring, depending on which force, gravity or spring, is acting. These do work to convert between potential and kinetic energies, and they can just go back and forth. In theory, they can do this indefinitely. So the idea of perpetual motion or perpetual motion machines is built around this. So if you have a pendulum, right, the pendulum swings back and forth. It goes up to a high point where it stops and it's got potential energy. Then it swings back through the middle and it's moving fast and it has kinetic energy. Swings up to the other side. Now we're back to potential. Swings back to the middle. Kinetic, potential, kinetic, potential, kinetic. So these forces can do work to go back and forth. Springs are also an example of this because if you have something bouncing back and forth on a spring, friction and drag have something to say about it, but in theory, with no friction or drag, you could get, I spelled perpetual wrong, but we'll have to deal with that. Perpetual, I'll just see, spell it right here. Okay. Um, Something like a spring as well, you could have an object on a spring that just bounces back and forth, and the spring gets compressed. Now you've got potential spring energy. Then the spring pushes the object back out, and it's moving as it moves the other way. And okay, now it's got kinetic, and then the spring starts to stretch out, and then the object slows down and stops. Now the spring is stretched, and you've got potential. Then it pulls back the other way. You're back to kinetic. The spring compresses and stops. Then potential to kinetic to potential to kinetic. So these conservative forces, they don't always do this. It's not like every problem with conservative forces will be going back and forth forever between potential and kinetic, but there's the ability for that to happen. So conservative just means you can keep going back and forth, changing the energy from potential to kinetic and kinetic to potential, and you can have that happen indefinitely in theory for certain scenarios. But that's conservative forces. So non-conservative forces, these common examples being force of friction, force of drag, or even applied force. We could talk a little bit about that. Um, do work resulting in energy changes that are not reversible. So here we had conservative forces, potential turns to kinetic, kinetic turns to potential. We can see that these are reversible in the fact that if you throw something up in the air, you throw it up and it has kinetic energy. Gravity does work that slows it down and turns it into potential energy at the top or apex. and then goes back and it starts to speed up again, and that potential energy from the apex turns back into kinetic as it falls back to the ground. Like a bouncing ball could, well, if you had no drag or friction or anything like that, um, it, depending on the right constraints there, you could have potential and kinetic energy just go back and forth, back and forth. Reversible energy changes, we don't see that with these forces. So a big one is kinetic to thermal. Once you have kinetic energy changing into heat or sound, you can't just put that heat or sound energy back into motion for the object, right? The air molecules themselves moving very quickly, and the energy sort of dissipated into the surroundings. So that's a common word we might see here is like we see this dissipated energy. And all that means is the thermal energy, rather than being contained within an object like a moving baseball, if that baseball hits a glove, a baseball player's glove, and creates a loud sound and a little bit of heat, that energy of sound and heat gets distributed, dissipated, and goes off into the surroundings, into the air and the glove and everything else. And it's not easy to just get that energy back and turn it back into kinetic. We can't really do that. Um, there's all kinds of energy changes that could be done with heat, and in fact we use geothermal energy for some of our like power and things, but um you can boil water with heat and then you can turn it into steam, and like the whole idea of a power plant is that the steam from heating water turns some turbines, and there you get kinetic energy out of heat. But um these non-conservative forces, we can't just easily put back thermal energy into kinetic. Same thing for a less common. You're really not going to see chemical potential energy, but the stored chemical potential energy in ATP in your body is used for applied force, and that turns into, well, usually kinetic energy if you, or you could also get this turning into thermal. When you use your muscles and you lift or push or pull and do some work with applied force, your chemical potential energy from your body turns into kinetic if you're moving something or moving yourself. Thermal energy as you produce heat yourself from your body functioning and doing the force, the applied force and doing work. So these energy changes are really not reversible. You can't just like, if we could take kinetic and turn it into chemical potential, you wouldn't need to eat food. You would just get hit by moving objects, and you'd turn their kinetic energy into potential energy for yourself, which might be kind of nice, but you'd get bruised a lot, I guess. So we can't just take kinetic energy and put it back into chemical potential for ourselves. We have to go through the specific process of, okay, we eat food and metabolize it and break it down and turn it into ATP. But applied force is an interesting example of a non-conservative force because our chemical potential energy for ourselves turns into kinetic or thermal, and we can't just like get it back. It's not this back and forth sort of process. So that's what we mean. And conservative forces fit really well with closed systems because you'll notice that um, one thing about these non-conservative, they involve energy types that are not in the conservation of energy. So thermal energy doesn't show up in our conservation equation. Chemical is just not really in there because we're not dealing with like the human body energy turning into something else. So you're mostly going to see these in like closed systems. They can exist in open systems too, but they're often indicative of closed systems. These definitely are more associated with open systems. Um, so we'll just say, how do we want to phrase this? Um, these probably indicate open systems, and these indicate closed. Although, yeah, I don't know how to phrase it because there can still be conservative forces in open systems. Absolutely, it's just like if your only forces are conservative, then um, actually, I don't know if I even want to. There's some weird things with gravity too. We'll just say often in closed systems. because there's situations like gravity we mentioned above. If you have a system that is just the object, then gravity is actually an external force. So there's definitely exceptions to that, and we're not always just going to see, oh, there's only conservative forces in closed systems, or there's only non-conservative in open systems. But there's a strong indication that, hey, if I've got some thermal energy here, look, I've got friction, I've got drag, maybe a person is doing some work somewhere along the way, and friction and drag are huge indicators that you've got that open system. Conservative forces, on the other hand, like gravity and spring, can very easily exist within those closed systems and still be doing work within the system, but not having any energy enter or leave the system. So it gets a little the crossover between, like, it's not all closed systems are conservative forces or anything like that. Okay, but that's conservative and non-conservative. It's just the energy changes that are happening, are they reversible, able to like go back and forth, potential to kinetic, then kinetic to potential, etc., or is it kind of a one-way trip? Kinetic to thermal, you're not really going to get that back in terms of turning thermal into kinetic or anything like that. Okay, let's see what else. That's mostly it. Yeah, and I know we haven't spent a lot of specific time on law of conservation of energy, but it really does it it pulls in a lot of this different, like, knowing systems, knowing whether systems are open or closed. That's important for conservation. Knowing work and the work equation for any work of external forces, especially when it comes to positive or negative work. That's important for conservation. Conservative and non-conservative forces, noting like, hey, I've got gravity or spring force that's just turning potential to kinetic or kinetic to potential, and that could very well be a closed system depending on the objects that are within it. Um, then looking at, like, all right, what is in my system? Is it an object earth system? Is it an object earth spring system? What is in this system? And based on that, is there going to be gravitational potential energy showing up in that system? Is there going to be kinetic? Is there going to be spring potential? So all these, there's many things that all kind of circle around or are adjacent to, important for law of conservation of energy. So when we're doing these problems, what it's a little tricky because you kind of have to have them all in your mind, or if you're studying up or referencing your notes, trying to keep in mind, okay, I looked at conservative forces, non-conservative. I looked at open and closed systems. We know energy types that are in a system. You need to have like earth and object to have gravitational potential energy. So yeah, all of this is different problems are going to have different focuses. One of the problems might be specifically asking you, is this an open or closed system? Another problem might want you to use the conservation of energy equation. Another problem might just look at work and say, like, what's the amount of work that's done? Or the work energy theorem is important here. Whenever work is done, there's a change in kinetic energy. So maybe we start off with a bunch of potential energy, and then we end up with a bunch of kinetic energy, because of the work done either by internal forces or possibly by external forces, depending whether it's an open or closed system. Um, so there's a lot of cycling things that are cycling around very similar to each other, of energy types, even just the equations like 1/2 mass times velocity squared. Okay, that's our equation for kinetic energy. Mg delta y for gravitational, 1/2 k delta x squared for spring potential. All these things are going to be relevant in different ways. So I think what's helpful is energy can feel like a lot. It can feel like, all right, here's all this bunch of information around this central topic of energy changes through work and the conservation of energy within systems, work being done by these various forces, conservative or non-conservative, and all of that can feel like just a bunch of information. I think it'll be helpful too once we start actually doing some problems. Then you can start to see, okay, this problem has force and displacement. All right, we're heavily focused on work here. This problem is looking at which objects are included in the system. So we can think about open or closed. Are there external, internal forces? What types of energy are going to be showing up here in this system? Um, Other ones will be like individual energy types. You might go in specifically and be like, all right, I have mass and velocity. Let me go ahead and find the kinetic energy. Maybe I'm looking at the change in kinetic energy for this system, which also connects to the work that's being done. So each particular problem will have information or what it's asking you or variables or numbers that will help us hone in a little more or specify what exactly we're looking at um, within these many topics and many tools that we have for energy changes in systems and applying conservation of energy to that. But yeah, conservation of energy is sweet because it is very useful for a large amount of problems. Now, one quick thing I might try to throw in at the end here is a little bit of graphing, just to get a bit of exposure to the types of graphs we would see. So we can actually see the law of conservation of energy on energy graphs. Let's draw a couple of those, and we'll do one here and another one over here. Now, most of these are going to have like energy. You might have a graph that is specifically just here's the kinetic energy and how the kinetic energy changes. A lot of them will just be energy in general. Um, Now, you could have position or displacement on here. So it says like as the object, moves a certain displacement, how does the energy change when it's like 2 meters away from the starting point, then 4 meters, then 6 meters as it's moving? You could have energy time. But in all these graphs, and we'll probably do some more details on graphs, like either in class. Graphs are a little tough because there's not as there's not a huge amount of them. Compared to Unit 1, where you see a lot of like velocity time, position time graphs, rarely acceleration time, but we see a lot of graphs in Unit 1 and not quite as many in Unit 3. Energy graphs are useful, they're neat, and you can see things like conservation of energy. They're just not quite as common as Unit 1. But we'll talk a bit about them here. Okay, one interesting thing to note is we could do different types of energy on this graph. So I'm actually going to go ahead and do a couple of, I think I'm going to do both of these as position. And we'll have this one be a closed system, and we'll have this one be open. Now I'm going to start off with, let's do blue for spring potential energy. We're going to say we start off with, we're going to say we start off with no spring potential energy. And actually, let's start off with a bunch. Why not? Let's start off with some amount. So here's your spring potential energy, specifically the initial spring potential energy. And this is an object that's like stretched or compressed on a spring. And as it moves, as it goes like to the right, we could say that our spring is launching an object off. Well, there's a couple things we could note. One is the farther and farther your spring is compressed, you get a lot more spring potential energy, and you're going to see a line that's something like this as the energy goes down, because our spring potential energy has a non-linear relationship with position or displacement. So let's write that equation over here. Spring potential energy, we know how to find it. It's 1/2 times the K value, the strength of the spring, times delta X squared. Because of that, now this graph is a little tricky to deal with because delta X here is, let's clarify, because this is going to seem wrong unless we do this. Delta X here is the motion of the object, not the compression of the spring. I'll try to draw a little visual here. Hopefully that'll help us out just to not, Mr. Barros is making terrible graphs. Let me see here. This is object, not the spring. Going all over the place with my writing. Object, not the spring. All right, we'll do a quick little image here. So here's a spring. It's all compressed. Here's our object. So the delta x we're looking at here is like the object moves from here to here, which as it does so, the spring would actually be less and less compressed. We'd get a smaller and smaller displacement for the spring as the object launches off of it. So I realize that that could be confusing with this graph, but we start off with a compressed spring. The compression delta x for the spring is very large, and we get a lot of energy. As that gets less and less, as we move to the right here, launching the object off the spring, we get a decreasing amount of spring potential energy, and it's a curved line because spring potential energy and displacement, or how far the spring is compressed, don't have a linear relationship, right? It's squared. So if your displacement is 2, or sorry, if you double your displacement, you will actually quadruple the amount of spring potential energy. So that's why we would see a curved line. Now, there's a really, really neat thing you can do with energy graphs, which is if we know this is a closed system and we want to draw the kinetic energy of the object, let's do that in red. Drawing that kinetic energy is actually really simple because in this closed system, at every single point along the graph, the total amount of energy, potential plus kinetic, needs to um, needs to remain the same. So our kinetic energy would look something like this. We would see a mirrored line of the spring potential energy, um, because as potential goes down, kinetic goes up. The spring launching the object off of it would turn the potential energy into kinetic through the work of the spring. And we're going to get a kinetic energy line that mirrors our spring potential energy. Okay. So just double checking the shapes of my lines. I know my curved lines are not always. I think that's right. This. Trying to visualize if we get a lot more. Yeah, the more compression we get. Yeah, I think that's right. Okay. Anyways, if I have to edit something on a curved lines, we can always go back and look at. There's some graphs that we'll do in some of our homework problems or Schoology problems that involve curved lines for. But I think I got the shape of the curved lines right. Okay. Regardless, when you have a curved line for spring potential energy on an energy graph, it shows the change in energy as your spring is more or less compressed. And the really cool thing with kinetic is we could just mirror that line, like a flipped version of that line, because now at all points, if we took here and here, or this spot here, or right here, or there, at all points along these lines, the total amount of energy, potential plus kinetic, remains the same. That's conservation of energy in a closed system. No energy enters or leaves. If we had 5 joules with 0, then we'd have 2.5 of each. Then we'd have like 3 and 2. And the total would be 5 joules at every single point along this graph because it's a closed system. Now, on the other hand, you could get something like gravitational potential energy. So maybe something starts off at the top of like a cliff or something like that. And this one's actually kind of nice because it's a linear graph. We can point out the reason for that because UG equals mg delta y. That is a direct relationship. Gravitational potential energy has a direct relationship with delta y. I guess we'd probably want to change this to a delta y. Let me just erase a little bit here. Okay, so delta y here. And as your object, this would be like a falling object. My line got a little curved at the end, but just pretend it's straight. For a falling object, it would start off with a bunch of potential energy up at the top of a cliff, or you drop it off of a table, or it's falling from some high point up in the air, and it's got a bunch of potential energy. All that gravitational potential decreases as it falls. I guess, yeah. I was trying to think of like you could say zero is. It's a little weird with this because you could say zero is the starting point. I'm going to draw an image, so this also could be confusing with displacement. If we say that this is delta y equal to zero at this spot, your positive delta y, you could define downwards as positive, which actually does something really cool here. When you define downwards as positive, which you don't always have to do, of course, but in fact, we often go the opposite. We often say down is negative, which is fine. Either one's fine. If we define down as positive, what that means is g, the acceleration of gravity, would be positive 9.8 or 10 rather than negative. And then delta y here would just be positive, right? As it goes farther and farther down, you'd be moving in the positive direction. So you'd get a positive displacement delta y. And that would match our graph, right? So looking at this graph, if you knew it was a falling object falling off a cliff, we'd say, oh, well, because the delta y starts at zero and then we go positive, they must be choosing down as the positive direction, which again is perfectly reasonable. You can absolutely do that. Okay, but I got sidetracked there because gravitational potential energy has a direct relationship. It's a linear or a straight line on the graph with delta y. And for this one, if it's an open system, what happens is as the object falls, it does gain kinetic energy. But open system would indicate there's probably some drag force going on here. Because if it's a closed system, there's no external work, there's no drag, there's no friction. All of the potential energy just turns into kinetic, and you'd get a nice simple like 10 joules of 10 joules of potential at the top turns into 10 joules of potential at the bottom. Easy. Open system means you will have a bunch of kinetic energy when you get to the ground right before you hit, because it's moving very fast, but you might see that there's not as much kinetic energy by the end as there would be if it was a closed system. So you'd see something like this. So sure, kinetic energy goes up and increases as gravitational potential energy decreases, but we don't end up with as much energy in the system as we had at the beginning. That's because drag force on the way down, if we're treating it as an open system, turned some of that kinetic energy into thermal. So we didn't end up with the full amount of kinetic energy the same as we started with. So both closed and open systems, I wanted to do the two different graphs to illustrate spring potential energy with its nonlinear relationship to displacement. We get curved lines for energy or displacement. Gravitational potential with its direct relationship, a straight line for an energy displacement graph, but also the closed versus open systems, right? Closed systems show at every single point in time, at every spot along the graph, the total energy in the system remains exactly the same. Open systems show, hey, we've got some energy entering or leaving, in this case, leaving our system, right? As we go on, as we go farther and farther towards the end here, we're ending up with less energy total in the system than we had at the very beginning because of something like drag or friction or some external force doing work that in this case removes energy from the system. Okay, so that's graphs is just, you're not going to see a ton of them, but they can often be, for closed systems, they can often be very nice and simple to draw because you just say, hey, once I get like the line for my spring potential energy on there, or I get my gravitational potential energy line on there, my kinetic is easy to draw because I simply mirror the other one so that at every single point, the total energy, kinetic and potential, remains the same. So those are kind of nice. And then open systems would also show with conservation of energy that, hey, we've got an open system and there's some energy entering or leaving. We don't have the same amount at all points. Okay. I think that just about does it. So we'll pause there. There's more to say on these. Again, there's a lot of central information to energy of like conservation and work and energy types and changes in energy and work energy theorem and open or closed systems and conservative or non-conservative forces. There's a lot going on there. So I think really one of the best ways to take all that information and start to really process it and work through it is to see some problems. So thankfully, we're at the point where you can actually now, with the three kind of intense information heavy videos we watched now, the first three videos in energy, we can do about 80 or 90% of energy problems with these. There's a little bit on power, and there's kind of some like side topics here and there, that some fringe topics that might get snatched up and addressed as we go. But yeah, these three videos cover really almost all energy problems. It's just a question of, as we approach those problems, how are we going to use conservation or energy types or work or conservative, non-conservative forces, open and closed systems, and all of this information? How does it apply to a particular problem? So, but we'll start doing that. We'll start thinking about which pieces and parts of our notes and our topics are relevant for certain problems. And it's cool. We'll start to see like multiple things. Like one of them is like a problem might be open and closed systems along with the conservation equation. Another one might be negative work done by friction along with the work energy theorem to look at changing kinetic energy. So we'll see combinations of these different parts of energy and work come together to form some solutions to problems. Okay, well, that should do it, and we will see you all in class. Don't forget to ask any questions. There's a Padlet on Schoology. You can put in questions that you have, and we can address them in class, or you can ask the questions in class. But definitely, if there's things that still feel weird from these, I'm obviously trying to. These ones are tricky too because I'm trying to connect those pieces in a way that makes sense. So if there's things that felt weird or didn't quite um, come across for understanding, let me know, and we can kind of clarify things and address them. And I think it'll help a lot to do some problems. Okay, well, that'll do it for the video. Thanks for watching, and we'll see you all around.